Assalamu alaikum, dear students. After covering Unit 5, today we'll begin a new unit, and that is Unit 6. If you do remember, we talked about the relationship between current and electricity and magnetism in Unit 5. And of course, using electricity with induced magnetism in Unit 5. And of course, the person or the scientist who discovered that we said it was Ørsted. And of course, found the relationship between the two, let's say. Or discover the relationship between the two, that would be more proper to say. And then today we'll talk about the reverse of this, or you can say the reverse engineering of basically Unit 5. Scientists, of course, wondered if we can induce magnetism from electricity. Can we do the reverse? Can we induce electricity from magnetism? And of course, they found out, or at least one of the scientists, let's say, started with let's say an answer yes to this question, of course, and that was Faraday, you can say. So what exactly did he do? We are going to discuss in this session, inshallah. So let's begin with this one. So, and of course, now that is basically called chapter 6, which is called electromagnetic induction. So basically, generating, you could say, or inducing electricity from magnetism, you could say. So what are we going to, or what are the chapter preview for this chapter? Of course, we can say electricity from magnetism. That is what we will be beginning with. That is basically for this session, inshallah. And then after that, we'll talk about generators, motors, and mutual induction. And then after that, we'll talk about AC circuits and transformers as well. And of course, each one of these are very, very important. And of course, you can say that chapter 6 is one of the longest chapters, not the most difficult one, by the way, yeah? But if you're following, and of course, if you're doing your, let's say, homeworks, and if you're following up, let's say, daily, and of course, you can get the marks that you desire, because most of the time you can see that a lot of marks will be in this chapter specifically. So let's begin with the first section, and that is basically electricity from magnetism. So like I said before, in chapter 5, we used to have, let's say, induced magnetism or magnetic field using electricity. And you do remember we said if current passes, or let's say flows through a wire, there will be a magnetic field around the wire, circular magnetic field, or concentric circle, or magnetic fields around the wire. If it is a coil, of course, there were magnetic fields, you can say, around the coil. And of course, the more the turns, the more the strength of the intensity of the current, you can say, the stronger the magnetic field were. But now, we can say in this chapter specifically, we're going to do the opposite. And of course, that is magnetic induction. So what are we exactly going to do here? And of course, I'll be drawing some, let's say, diagrams to help you understand this better. But the first thing is, it is possible, just remember this, it is possible to induce, right, to create a current in a circuit without the use of battery. So you might wonder, for example, how can I have electricity in a circuit without the using of battery, let's say, or without using any external power supplies, let's say? Well, we can do that, okay? So if we can do that, what are the ways, or how can we do that? All right, well, basically, like we said, that you've learned that the current is in a circuit is the source of a magnetic field. That was chapter 5, we can say. Now, conversely, right, we can say the reverse or the opposite is also true. A current results when a closed circuit is basically moves with respect to a magnetic field. Now, of course, I'll explain more regarding this one right here. If neither, so how does it work? Let me take you to the whiteboard and explain this to you. So imagine or consider this, or in chapter 5, of course, let's say we had, we had an alternating source, let's say, and of course, let's say we had a resistor as well, or you can say a variable resistor. Using all this, of course, we used to have, let's make this on a coil as well. Let's say here's a coil. And having, of course, all this, let's say, once you turn the switch on, of course, there were a magnetic field around the coil here. So that was chapter 5, right? Creating magnetic field, let's say. And of course, there's a magnetic field here around the coil using electrical current, you can say. Okay, and then that, of course, that is a direct current. That is, let's say, where the current doesn't change. And of course, you can use an AC. If you use the AC, the polarity of the magnet change. And of course, we used to use the right-hand rule to tell, for example, which direction is which. Like which side is north, which side is south, using the right-hand rule. Now, or today, or in this session, we're going to do the reverse of this. We're going to use, let's say, a magnetic field to induce electrical current. So how are we, or how can we do that? All right, so this is how we do that. Let's say we have a coil. Here's a coil, okay? And then this coil is connected to, let's say, a galvanometer. Okay, and of course here's zero indicator, let's say point or zero indicator. Let's say this side is positive, the other side is negative, and here's the needle. Normally, if there's nothing close or surrounding the coil, this galvanometer shows zero. That means indicating that there is no electrical current, let's say, through the circuit here. But what happens if I, let's say, bring a magnet close to, what happens if I bring a magnet, let's say, close to this coil here? So let's not this one here. So let's say I have a magnet here. So, and this is obviously north and this is south. So what exactly happens if I bring this magnet close to this coil? So, but that is not the, let's say, the whole thing here. In order for us, let's say, this is basically what you can say Michael Faraday, you can say, did, all right? Or the Michael Faraday, you can say Faraday's experiment of, or you can say electromagnetic induction experiment. So here's what he did. He brought a magnet, all right, you can say closer to a coil. So if we bring this magnet closer to the coil, all right, so if it is, let's see if we can, let's move the whole thing, yeah? So once you move this magnet closer, let's say, to the coil, and then back, let's say, or away from the coil, as long as there is relative motion, let's say, between the magnet and the coil, of course, there will be induced electro, or you can say electromotive force here, or you can see that the galvanometer needle will shift or change. So let's say this is the magnet first, and of course we do have, let's say, regarding the magnet, we have, you know, like these are the directions of the magnetic field, and you do know that these directions are going from north to south. And of course, it is, if it is inside the magnet, that is going to be from north to the south as well. So that'll be a complete, you can say, cycle or loop through the magnet as well. Okay, so this is the magnet basically. So once again, what happens if I bring this magnet closer to the coil here? So once I do this, you can see that these magnetic field lines are cutting through the coil. Cutting what? Cutting through the wires of the coil, you can say. And this, of course, using or remembering chapter 5, of course, these coil, or you can say the wire of the coil, has free electrons. So once you're moving this magnet closer to the coil or into the coil, let's say, these magnetic fields, let's say, will apply a force on this, like on the free electrons that are inside the coil. Once there's a force applied, of course, using, let's say, chapter 5 ideas. By the way, there's a huge relationship between chapter 5 and chapter 6. So if chapter 5, you can consider chapter 5 to be a foundation or a good foundation for chapter 6. So I really hope you understand chapter 5 very well. So going back to the topic here. So these magnetic field lines, of course, they apply a force on the free electrons that are inside the conductor here. And this force, of course, makes them to be able to move. So once they're moving, then of course you would see that this galvanometer needle, it is going to deflect, let's say, or it will show, let's say, it will show positive, let's say it will deflect and shows this one here. Let's just say positive 1. Let's just, for the sake of the example here. So that is what happens. Now, as soon as you, let's say, stop the magnet from moving, you will see that this galvanometer needle, of course, now it is going to deflect, or it is going to back to 0, or you can say the needle will be going back to 0. So, and then after that, when you, let's say, pull the magnet out of the coil here, okay, when you pull the magnet outside the coil here, you will see that the galvanometer is again shifting, but this time here, it is going to shift in the opposite direction here. So this time it is going to shift, but in this direction. So once again, once we, let's say, insert the magnet into the coil, you will see that the galvanometer shifts to the positive side. By the way, at this point, it really doesn't matter like which side is which, like when will it shift positive, when will it shift negative, yeah? So just remember this, when you insert the magnet into the coil, just remember that the galvanometer needle will shift to one direction, and then once you move the magnet, let's say, away from the coil, then this galvanometer needle will shift in the other direction. So what does the movement of the needle or galvanometer needle tells us? It tells us that there is an induced current through the circuit, or in another way you can say that we have induced electromotive force, you can say, or simply you have induced current through the circuit, because this galvanometer needle shifting, let's say right left, that means there is an electrical current through the circuit. This electrical current through the circuit is called induced current here. Okay, so what happens if I, let's say, reverse the magnet, by the way? So if I reverse the magnet, let's say this time, we'll switch this one with, let's say, south at this side first, and then of course north at the other end, but then I'll have to reverse these directions as well, because the direction of these are going from north to south, yeah? So this is what you see here. These are the directions now. So what happens if I move this magnet, let's say, into the coil or closer to this coil here? So once I do this here, and of course you'll see that the galvanometer needle is again shifting, it is moving, but this time, in the previous time it was, let's say first time, it was shifting. The first time, if you do remember, it was shifting to the positive side first, yeah? Then that is when we brought closer. And then when we went, for example, when we like removed the coil, the magnet, sorry, then this galvanometer needle were shifting the other way, or you can say negative. And of course, if there's no motion, or if it is too far, it shows 0. But you can see, if we switch the polarity of the magnet, you'll see that this galvanometer needle, it is starting to shift first to the negative side, which is opposite to what happened in the first place, let's say. So if that is the case, what happens if we move the magnet away from the coil? Then of course this time it is going to shift to the positive direction right here. And then there was another question. What happens if I move this magnet like at a faster rate closer, let's say, into this into the coil? Then you'll see that the galvanometer needle will be, let's say, if it is let's stick with the south and north side here. So if we move the magnet at a faster rate into the coil, you'll see that this galvanometer needle will be shifting, you know, like more, or it will be deflecting more, which indicates that the faster the movement, the more electrical energy, or not electrical energy, let's say, the more the current will be induced. And of course, it is the same thing if you move it away faster, you'll see that it will deflect higher, indicating that the induced electromotive force that is generated now is higher compared to the previous time, which we moved the magnet, let's say, slower into and out of the magnet. But there is also one more thing which is very, very important. We'll say this is true always as long as the magnet, let's say, and the magnet and the coil are in a relative motion. What do we mean by this? You could have the magnet inside the coil, but if there is no motion, or we'll say this, if the magnet is at rest, no movement, let's say between the coil and the magnet, then there will be no induced electromotive force. So based on this, we can conclude, as long as there is a relative motion between the magnet and the coil, there will be induced electromotive force. There will be induced current. But if there is no relative motion between the coil and the magnet, then of course there will be no induced electromotive force. And that is if we both, let's say, if we move both the magnet and the coil at the same time and at the same rate, let's say the same speed, either, let's say, to the right or to the left, as long as we move them the same or at the same rate, if there's no relative motion between the two, then there will be no induced electromotive force. And that is obviously, you can say, what happens when you bring a magnet closer to a coil, or once you, for example, let it rest inside the coil, or once you pull the magnet out of the coil. So remember this. If you're, let's summarize this real quick. If you insert the magnet, the galvanometer needle will shift in one direction. If you pull it out of the coil, the galvanometer needle will shift in the other direction. And if you hold the magnet still inside the coil, where there's no relative motion between the coil and the magnet, then we'll say there is no induced electromotive force, and that is where the galvanometer needle reads 0 here. So basically, that is what we have learned. Remember, we went through this point. That was, we said this is, well, that was chapter 5. Electricity is the source of the magnetism. That was chapter 5. Conversely, that is what we have in this unit. A current results when a closed circuit or electric circuit moves with respect to a magnetic field. So as long as there is a relative motion between the magnet and the coil, then we'll say there will be electromotive force induced. And this electromotive force, if we have a closed circuit, would lead to a current circulation through the circuit. If neither, so you can see, this is also very important, if neither the magnet nor the circuit is moving with respect to one another, no current will be induced or present in the circuit. If the circuit moves towards or away, don't forget it. If it moves closer, or you can say towards or away from the magnet, or the magnet moves towards or away from the coil, or you can say from the circuit, a current is induced. So we can say, as long as there is a relative motion between the coil and the magnet, there will be induced electromotive force, or you can say induced current as a result of that as well. So we can summarize that as well. We can say as long as there is a relative motion between the two, a current will be induced, in the circuit. So we've been talking about electromagnetic induction a lot. So I hope you have an idea by now. But what is the true definition, or how can we define electromagnetic induction? We can say electromagnetic induction is the process of creating a current. So what is it? It is a process of creating a current. But can you have, or can you create a current without creating an electromotive force, a potential difference first? The answer is absolutely not. So we'll say electromagnetic induction is the process of creating a current in a circuit loop. But how do we do that? By changing the magnetic flux, let's say, in the loop. So if you do remember here, now we were talking about this. So basically we said if you do this act, you'll be basically inducing or producing electrical current, and that is called induced current. But why does it exactly produce a current? Because once you're doing this, clearly you are moving, let's say, this magnet closer, let's say, to the coil, or once you move it away from the coil, there is a magnetic, there is a magnetic field you can see around the magnet, and this magnetic field here, let's say, let's draw some more here. These magnetic field lines are obviously, like acting, let's say, or applying, let's say, to the cross-sectional area of the coil here. So of course we've learned that magnetic flux equals to AB cosine theta. Yeah? So of course once you're doing this, once you're bringing this closer further, you are changing the number of the magnetic field lines that are crossing the cross-sectional area of the coil. So this difference, or this change in the magnetic field lines crossing the area of the, let's say, the cross-sectional area of the coil, that would induce a change in the magnetic flux. And as long as there is a change in the magnetic flux, we can say there will be an induced there will be an induced electromotive, or there will be an induced electrical current through the circuit. And of course, like once again, we cannot, or we will not be able to have or to induce a current without inducing electromotive force first. Okay, so this is the reason why this induces electrical current, or induces current. That is because this act will change the magnetic flux, you can say, or changing the magnetic flux across the cross-sectional area of the coil. That would lead, of course, to the induced electromotive force. But of course, the reason why this happens, because these magnetic field lines, you can say, affect or apply a force on the charges that are within, or the free charges that are within the coil. And of course, that was for the electromagnetic induction. So once again, what is electromagnetic induction? It is the process of creating a current in a circuit loop by what? By changing the magnetic flux in the loop, you can say. That is one. What about the induced current? Remember this. Whenever there is a change in the magnetic flux, let's say, of course, there will be always an induced, let's say, electromotive force, or you can say a potential difference, or you can say a voltage. Yeah? But remember this voltage, if you don't have a complete circuit, will it be able to create a current so that it can flow through the circuit? The answer is no. So in order to have, let's say, a induced current through the circuit, you must have a complete circuit so that the current can circulate or flow through the circuit. Remember, if there's a gap within the circuit, then you can still have the potential difference produced or induced, let's say, that is electromotive force. Yes, but if the circuit is not complete, then of course you cannot have the current that can flow through the circuit. So these are different ways where we can produce, let's say, induced current here, or produce current here. So there's a magnet. Simply by bringing this magnet closer or away from the coil, you can induce current. And of course, this galvanometer would be a very good indicator to tell us whether current is induced or not. Another way is, by the way, we said, if you remember, as long as there is a relative motion between the two. So it doesn't matter which one you move, yeah? You could hold the magnet still, but move the coil, like closer to the magnet, and then or away from the magnet. As long as there is a motion between the two, that induces electrical current, you can say. And of course, at this situation here, you can see that the magnet is stationary. What we do is we'll move this wire up and down here so that we can induce electrical current. But let me give you an idea here first. You can see that this arrow upward, yeah? So you will be inducing maximum current if these wires perpendicularly cutting through these magnetic fields, okay? Because in that case, of course, you will get maximum electromotive force, you can say, and of course, in turn, maximum current that is induced within the circuit here. If you have a specific, for example, or a limited, let's say, certain length, and of course, let's say, obviously we have one n, or you can say the number of turn here is just one. But imagine or consider this here. What would happen if we move the wire parallel to the magnetic field lines? In that case, would it cut any magnetic field lines? The answer is no. Then of course you wouldn't be able to induce magnetic, or you can say induced current, or induced electromotive force in this case. But of course you could have, let's say, induced electromotive force if you were moving this wire at certain angles here. So for example, starting from here, let's say, instead of moving it horizontally, and not, let's say, let me show you like perhaps a better drawing here. So we said first place, or first time, if we move this wire parallel to the magnetic field line, then of course there would be no induced current here. And it will be maximum if you move the wire, let's say perpendicularly, downward or upward, as long as it is within the magnetic field. And then, so we can say this one as well, that creates maximum electromotive force here, maximum current at the same time as well, we can say. And of course, we can induce current as well if you move this one within the magnetic field, but tilted at a certain angle. But of course, that will not give you the maximum electromotive force. It will give you some, or it will induce some electromotive force, but it's going to be bigger than zero, but less than maximum. It will be maximum when this wire cuts the magnetic field lines perpendicularly. What about this one here? So basically, these are two methods of generating electrical current. And of course, this is the third one here. What happens here is basically now, these are the magnetic field lines going from north to south. What we do here is basically, we're turning the coil inside a magnetic field. Once you're turning the magnetic field inside, or this coil inside a magnetic field, you're changing the angle. Remember this? We said the flux is equal to AB cosine theta. So basically here you're changing the cosine theta, or you can say the number of the magnetic field lines that are cutting through the coil, or the angle for that, yeah? And of course that would also changes, or you can say there will be a change in the magnetic flux. This change in the magnetic flux across the coil, you can say that will induce electromotive force. And of course you can see this galvanometer indicating that will be maximum, let's say, and of course 0 when the angle, you can say it is, or this perpendicular, let's say, or you can say the coil is vertical if it is this coil, and then of course maximum when it is parallel. You might say, but why is it parallel? Because in this case, of course, we will consider the direction of the edges of the coil. So you can see, if I consider this edge, it is moving perpendicularly downward, just like this wire right here. We said we'll get maximum if it is downward. That is for later when we talk about, let's say, generators, but just have an idea for now. We can have maximum, minimum, and of course maximum, but in the negative direction as well. So these are all the process of, let's say, generating electromotive force. And of course, these are extra, you can say, these are more about this, but of course, in a different way. Not in a different way, actually. I can just go through this one real quick since I've already mentioned this. Yeah? Imagine there is a magnet, there is a coil, there is no motion. If there's no motion, the indicator reads 0, indicating that there is no induced electromotive force here. What about this one? Once you move this one, let's say, towards left, you can see that this galvanometer needle is shifting to the right. All right, you can call it positive if you like. So that is when we move the magnet closer to the coil. Here, now the coil is kept stationary. The coil is at rest. If it is at rest, the indicator reading 0, that means there is no induced electromotive force. Now we're going to move away from the coil. First, remember this, we move the coil to the left. Now we're moving the coil, let's say the magnet, sorry, we move the magnet towards left. Now we're going to move the magnet to the right here. You can see that the galvanometer is shifting, but opposite to what we have here. Okay, now what about this one here? Higher speed. If you look at the indicator here, now that was basically, these two you can say are similar to one another. Okay, so that is both, let's say, we'll move the magnet both to the left. As you can see here, this is basically the indicator. If we go at a higher speed, you can see that it's almost like at the end of this scale here, indicating that the strength of this current that is induced is higher or bigger than the one at this. Why? Because there's a higher speed. So the higher or the faster the rate of the motion here, then the amount of electrical current that is induced will be higher there. And then what happens if we switch the polarity? So previously was north, now we switch this one, we'll say south first. You can see that it will shift in the other direction. All right, so that is for this one as well. Okay, so By the way, there are a lot of YouTube videos you can watch, of course. It tells you how these are formed, especially with a galvanometer, let's say. And these are very cool experiments, and I really want you to, like do some searching and, of course, watch some of these experiments. You will be surprised how these, how fun they could be. Okay, now new, like diving deeper into why exactly or how these electrical, let's say, or these electromotive force will be induced, and then how that would lead to a current circulation through the circuit here. So we have the induced electromotive force in a straight conductor. When we say the induced electromotive force, that is obviously a voltage here, but then later on this voltage, if we have a closed circuit, would lead to a current through the circuit as well. So remember that one. But there's one thing, as long as you move a conductor within a magnetic field, there is always induced electromotive force, as long as there is a relative motion between the two. That is the key point, so I really don't expect you to forget this, yeah? But then also remember this, if it is just a conductor within a magnetic field, if this conductor is not connected to any external source, then the only thing you get is just the potential difference, just a voltage, and that voltage, we call it induced electromotive force, all right? We will not have or get the current. Why? Because you can see that this is not connected or it is not a closed loop. We will only have a closed loop if there is a path for the electrons so that they can circulate in the circuit. Okay, so let me tell you more about this. Okay, so consider conducting wires pulled through a magnetic field as shown in the figure here, that is 6.2. Okay, so basically we have this conducting wire, which is, let's say, moved in this direction here. And of course, this is a magnetic field. You can say these magnetic fields are pointing outward, so the direction of the magnetic field is outward, which is towards you can say. Okay, and then charged particles move with a velocity at an angle to the magnetic field will experience a magnetic force here. And of course, this magnetic force, according to the right-hand rule, if you do remember, we said for positive charges, and this is what exactly we're going to use. Remember, use the right-hand rule. We said V or thumb in the direction of the motion here. That is the velocity here. Your fingers, that is the direction of the magnetic field here. We'll say if we have charged particles here, if it is positive, the force on that charged particle, of course, it is going to be out of your palm here. So, which in this case is going to be downward. And the forces, and this force on negative charges, it is going to be upward. Remember, we're talking about a conductor. So conductors normally, they are neutral. That means they have equal amount, let's say, positive and negative charges in them. Okay, so take a look at this one here. Let's say we have a lot of, let's say, or positive, negative, let's say positive, negative, and then positive, negative as well, yeah? So these are, let's say, the charges that we have, and of course now we can say this conducting material is neutral. But once you move this one through a magnetic field, there will be a force on these charges here. And if the charge is positive, we said the force on this charge, because remember, using the right-hand rule, if the charge is positive, the force on them will be downward. If the charge is negative, the force on it will be upward here. So we can say that all these charges that are negative, of course, will pile up at one end, sorry, not positive. All these charges will pile up at one end of the conductor, and of course these charges are negative. And then the other side of the conductor, it is going to be positive charges right here. And of course it is a wrong thing to say positive charges moving, but this is just for the sake of the explanation. We do know that electrons are moving. Once electrons left from this side, only positive charges will be left, or you can say the positive, let's say atoms, nucleus will be left. So of course we can consider this side to be positive, the other side with a lot of electrical charges or with a lot of electrons, we call it negative. But look, doesn't this look like, or it looks similar to something that you've seen before? And that is a battery, okay? So if we have a single cell, let's say, if it is just a single cell, or if it is just one, we can call it a cell. But we'll just go with battery for now. So isn't that looks like a battery here? So this is just the same as this. So if this is a battery, of course, this is positive, this is negative. Or you can say, if I draw a battery here, of course, this side is going to be positive end of the battery, and then the other side is going to be, let me draw this, erase this one so it doesn't confuse you. And of course, this side is the negative end of the battery. So this act is basically, or you can say up to this point, we have induced electromotive force, or you can say a potential difference, or a voltage, you can say, to be more specific. But the voltage that is produced here, of course, we're going to represent it with, you can say this letter, of course, And this letter now, it is representing the, you can say the voltage here. So this is the same thing as the, you can say electromotive force, that is from the source you can say, or the voltage. And of course, at some points you can call it potential difference as well, but potential difference would normally be across the devices. But just to help you that this is a voltage now. Let me just erase this one here. Okay, so electromotive force is the same as, you can say, the voltage that is induced. But the voltage normally, when we induce a voltage, of course, we give it this letter here. Okay, so this is basically what we have, or how we can induce a voltage. But here's the second thing here. Now, does any current flow through this wire? The answer is no. Okay, so when can we make this wire, or the current in this, to flow in a circuit? Then of course we can have, let's say, or use that electricity that is generated if we connect this one to an external source, an external circuit, let's say. So if I have a circuit here, let's say if I have a light bulb here, and of course now this light bulb can glow, all right, even though it might be dim a bit, because perhaps the strength of this electromotive force that is generated is not too much or too high. But if you connect one wire, let's say from this end to the other one, and of course now current will flow from the positive end, let's say, to the negative end. But if it is electrons, electrons would normally move from the negative side to the positive. So you have to differentiate between the two things, between the direction of the electron movement or the conventional current movement. Normally current will flow from, we'll say conventional current will flow from positive end to the negative. But electrons will flow from negative to positive. Okay, so this is how we can induce or generate electrical current here. Or this electrical current that is generated, you can call it induced current here. Okay, that is basically from the magnetism. All right, so we went through all this. Yeah? This effect is equivalent to replacing the segment of a wire and of course the magnetic field with a battery that has a potential difference or electromotive force between the terminals. But remember this, as long as the conducting wire, it's very important because we've mentioned like seconds ago, yeah? We've mentioned as long as there is a relative motion, back then we were talking about a coil and a magnet, yeah? As long as there is a relative motion between the magnet and the coil, you will induce, or you will get induced electromotive force. We can repeat the same thing for this situation as well. We can say as long as the conducting wire moves within, inside the magnetic field, we will get electromotive force. We will induce electromotive force. But as long as this wire stops moving inside the magnetic field, or as long as, let's say, for example, as soon as it gets out of the magnetic field, then there will be no induced electromotive force anymore. All right, so just remember this point very carefully. Okay, so that would be for this one here, but there's also something very important. So we said this side becomes negative, the other side becomes positive. Now here, let me ask you a question. What happens if we move the wire, let's say, the other way around? So of course now these polarities will be different here. So it's not like always this side is negative, the other side is positive. No, that depends on the direction of the magnetic field. That depends on the direction of the motion as well, because you've studied that, all right? Well, you will have to adjust, let's say, your hand just like, for example, this one. So remember this, if the motion were to the other side, let's use this one here. Let's make it white. Let's erase this one for now. Let's say, what happens if the motion were in the other direction here? If the motion were in this direction here, so what would have happened here? Okay, let's make this one thinner a little bit. So what would happen if the motion were in the other direction? I think otherwise the other one here. So let's do that. Okay. All right, so let me make, or cover this one. So once again, what would have happened if the direction of the motion were in this direction here? So of course now, previously, this is how we, let's say, held our hand. Now we'll have to flip it in this case. So if that is the case, remember, using chapter 5 directions, or you can say right hand rule, this is the direction of the motion, you can say. That is the velocity. This is the direction of the magnetic field, which is towards you. Then in this case, of course, if that is the case, then the positive charges will be on top, or you can say at the top of the conducting wire, and then the negative charges would be below here. That is, for example, so you see how or why when, for example, you move the wire, or if I take you back to the coil, if you take, let's say, move the coil into one direction, you get a positive one, yeah? But if you, for example, let's say, reverse the direction or pull it back, or let's say out of the coil, the direction will be reversed, and that is, of course, because of this one, because you can see the direction of the force on the, or you can say the force on the direction of, or you can say the force on the charged particle will change, or you can say the direction of that force change, of course. This is why positive and negative swap, you can say, or the polarity of this will switch. That is, remember this, we've just covered if you move to the right or to the left, correct? No, actually, we've done the opposite here. So basically, this is to the right, and then the other side is to the left, yeah? Okay, so that was for a magnetic field pointing outward. What if the magnetic fields were, let's say, into the board, into the paper, and then you move to the right or to the left, and of course that would also reverse the direction of the, let's say, the current that is, or the electromotive force that is induced within the conducting wire as well. So you can see that the separation of positive and negative charges, or moving charges, by magnetic force creates a potential difference. This potential difference is called electromotive force between the ends of the conductor. But remember this study tip, which is also very important, says what? Moving a conductor inside a magnetic field will always produce, as long as it is a conductor, it will always produce an electromotive force. It will produce a voltage. But it will not induce a current. So when will it induce a current? It will induce a current only if we have a closed loop, or if you connect that conducting wire into, or let's say with an external source. What source? An external circuit, let's say. Okay? So we can say, remember, moving conductor inside a magnetic field produce an induced electromotive force whether the conductor has a closed loop or not. But a current will only be induced. For current is different, because we're talking about current is the flow of the electrons within the circuit, yeah? So if the circuit is not connected, they're not able to flow or circulate, move through the circuit, so there will be no current here. So now we've mentioned how we can induce electromotive force, yeah? But so far we haven't mentioned what would be the strength, yeah? What is the size of this voltage that is induced within that conducting wire here? And of course, now we have an equation, yeah? We'll say the magnitude of the induced electromotive force within that conducting wire can be found by using this equation, which is electromotive force that is induced, of course, is equal to B times L times V sine theta here. Okay, so what are these terms that we're using here? So B, that is the magnetic field strength, the strength of the magnetic field. So we will say the electromotive force that is induced is directly proportional to the strength of the magnetic field. In another word, right, or in other words, you can say the stronger the strength of the magnetic, the stronger the strength of the magnetic field, the more the induced electromotive force here. And then, of course, another let's say thing that it depends on is the length of the wire. Okay, so we can say the longer the wire within the magnetic field, the more the induced electromotive force as well. Okay, so that'll be for this one as well. But remember this. If you're given, let's say in a question, all right, let's say you're given a wire, a conducting wire, let's say, that is 10 meters long, let's just say, yeah? But only 5 meters of this wire is within or inside a magnetic field. So what length are you going to use? Will you use 10 meters, like the length of the entire wire, or just the length of the wire that is within the magnetic field? And of course, you'll have to use the length of the wire that is only inside the magnetic field, not the ones that are outside. So just be careful in that case. Of course, you'll have to use just 5 if it is in meter. Okay, and then we have velocity, like how fast you're moving this wire within the magnetic field. Because the faster, which is the same thing as we have mentioned previously, we said the faster the speed of the coil or the magnet that, or the faster the relative motion between the coil and the magnet there, we said the higher the induced electromotive force there, or the higher the induced current over there for coil and magnet, yeah? That when it was connected to a galvanometer. But now we can say, because we just have a wire, so we'll say the faster the rate or the motion of the wire within the magnetic field, the more the induced electromotive force. So we can say the induced electromotive force also depends on like how fast this conducting wire it is moved within inside the magnetic field here. And of course, we'll say sine theta as well. And that is, of course, you can say the angle, right, between the magnetic field here and, of course, the velocity that you are moving the wire with. Because remember this, we said if this wire, like previously I've showed you, let's say the wire when it was connected to a galvanometer. So we said if wire cuts the magnetic field, let's say at perpendicular, we get maximum electromotive force. But if it is at some angle, it will be less. If it is parallel to the magnetic field line, then of course we get zero electromotive force. So of course this angle is basically this sine theta. That is the angle you can say between the magnetic field and the velocity that you're moving the wire with. That all determines the strength. And of course we can say this electromotive force also directly proportional to sine theta as well. Once again, this sine theta is the angle between the B, magnetic field strength, and the velocity as well here. Okay, so, but there's one more thing that I haven't mentioned so far. What is the unit of the potential difference, or what does the potential difference or the voltage is measured in? Voltage is normally measured in volt, yeah? Or electromotive force is measured in volt. Let's say, of course, determining we're using this equation for. But then, what about the magnetic field strength is measured? Is measured in Tesla. What about the length? That is measured in meter. What about the velocity? That is, of course, measured in meter per second here. So, based on this, so we can say voltage equal to Tesla meter times meter per second. Meter per second. So, of course, now I can summarize this one. I can say voltage, right? It is equal to Tesla meter squared over the second. But if I want to find Tesla here, I can say Tesla, it is equal to what? We can say Tesla is equal to voltage second over meter squared as well. So, of course, remember this because you might need this in the exam. Okay, of course you do, okay? So, just remember, these are what, the definition of each one of these terms that are being used here. Okay, so what does, we have a question now, it says, what does the induced electromotive force depend on? The induced electromotive force, whenever you get questions like this, always write the equation. We said it depends, or electromotive force was, okay, electromotive force equals to what? Equals to B, I, all right, or not I, B, LV, okay, B, oh, that's not L, once again, magnetic field times the length of the wire times the velocity, and then of course sine theta as well. So we can say the induced electromotive force depends on the strength of the magnetic field, that is measured in Tesla, don't forget, the length of the conducting wire, that is, these are basically directly proportional, and also the velocity at which the conducting wire moves through the magnetic field, that is also directly proportional, and then of course the angle theta, which is between the direction of the motion and the magnetic field as well. Okay, so these are the four factors that this induced electromotive force depends on when it comes to generating or inducing electromotive force. Now we have a Zhyar question says, which of the following equations correctly, or let's say correctly to calculate the maximum induced electromotive force? And of course, which one of these would be your best option? When we say maximum, that means sine theta, or theta is going to be 90 and sine 90 is 1, so you don't have to write sine theta in that case. So of course, we will say electromotive force, it is basically maximum when it is basically B times L times V. Okay, because remember, we're not writing the sine, because sine maximum is, or sine 90 is 1, and that is when it is maximum. Okay, now let's talk about another concept which is also very important, you can say, or another important factor that affects the induced electromotive force, and that is basically the angle between the magnetic field and the circuit affects the induction. So what exactly do we mean by that? Like we've mentioned previously, something very important, yeah? The angle at which, let's say, you're moving, or let's say the angle at which the conductor is cutting through the magnetic field lines, or it could be the magnetic field lines that are cutting through the conductor, let's say. All right, as long as there is a relative motion between the two, we don't care which one is moving. As long as there is motion between the two, there's always induced electromotive force. And of course, let's say the bigger the sine of the theta, in that case, let's say from 0 to 90, the bigger the angle in this range, we can say the bigger the induced electromotive motive force in there. Okay. All right. So take a look. Now we will get, or you can say the induced current is maximum. When is it maximum? It is maximum if the plane of the loop is perpendicular to the magnetic field line. So now take a look at this one, of course. Let's say here is just for example the same as in this diagram here. So you can see these are basically magnetic field lines here. So you can see that these magnetic field lines that are coming out, let's say of the screen, let's just say, okay, these are basically, or we will get maximum electromotive force or induced electromotive force. And when these, you can say these are basically, these magnetic field lines are cutting through the plane of the coil. In this case, of course, you're moving this coil to this direction. So you can see here, this coil, or we can have, or if we have a paper or something like this, if let's just say this is one side of the coil, that is, let's say this side right here. So watch this. If I move this one here, this pen, obviously, it is going to cut through the magnetic field lines. You can say cut most of the magnetic field lines, or all of it if not, yeah? So this will induce a maximum amount of, let's say, electromotive force. That is the first one. Yeah? Or if not, you can take a look at this one here. So when you are moving this coil, let's say, okay, remember, you have to move it either upward or downward. If you move it this way, that is moving in the same direction as the magnetic field line, so no induced current. But just consider, if you move this coil here, up or down here, so this coil is basically cutting through these magnetic field lines. And if these magnetic field lines are cut, of course, then we can say we have maximum induced electromotive force here. If not, you could just say the angle, all right, imagine this is the direction of the motion here, and this is the magnetic field line. We said that, if you do remember, we said electromotive force induced here, it is equal to BLV, and of course, sine theta. So we said this sine theta is between the two here. So this is the direction of the magnetic field, and of course if this angle is 90 here, if this is the direction of the motion here, so the angle between the two is 90, then of course we get maximum amount of electromotive force here. That is the first one, yeah? So take a look at the second one. It will be smaller if the plane is tilted into the field, as in B. So this electromotive force that is induced, of course, it is going to be smaller if we're going to tilt this coil, or if this coil is moving at an angle, let's say, or cutting these magnetic field lines at an angle here. So if you remember previous time, we said if it is like this. Now imagine if I tilt this pen here, something like this, yeah? Or perhaps I can do it this way as well. If I, let's just say actually this way would be better. If it is cutting these magnetic field lines at an angle here. So you can see the bottom of the pen is closer to the screen compared to the tip, so that means there is an angle here. Okay, if not, you can take a look at this one here. So let's say this is the direction of the motion here. Or if you're trying to move this one here, at some point, let's say this way here. So you are still cutting through the magnetic field lines, but at an angle. And of course, that angle, if that is the case here, we will say that the electromotive force that is induced is not going to be maximum. But of course, we do have some, so we cannot say zero as well. But if we look at the third one, the induced electromotive force will be zero if the plane is parallel to the field. So that is something you really have to be careful with and notice this. So take a look at this field line here. Of course, you can see that. These are the magnetic field lines are outward, you can say out of the screen here. But I'm moving this one like in this direction here. So in another word, you can see that if these are the magnetic field lines here, so I'll be just moving the coil just like this one, which is basically parallel to this. So you can see that there is no cuts, there's no interaction between the coil and the magnetic field line. And of course, this does not produce an induced current. Now, take a look at this one, which is perhaps it's more obvious. If this is basically the coil, this is, you can say, the direction of the normal to the coil. So you can see this is the direction of the magnetic field. And if we move the coil this way, you can see that these two are parallel to one another. So they are not cutting one another. And if they are not cutting one another, then of course there would be no induced electromotive force in here. And of course that doesn't induce any electromotive force. So how do we summarize this? The electromotive force that is induced will be maximum if the coil moves, let's say, or if the coil is cutting through the magnetic field lines at a right angle. That's one thing. And then, or you can say another way actually, you could say if all these magnetic field lines are perpendicular to the cross-sectional area of this. Okay, you can see, or you can say perpendicular to the plane of the area. That is also true. It is less when it is at some angle, it is zero when these two are parallel to one another. Okay. And I'm afraid that'll be it for today. next time, inshallah, we'll continue from these questions, and then after that, we will explain the change in the number of the magnetic field lines, and then afterwards. So till then, keep practicing, and I really hope that you can answer these questions before I answer them in the next session. So till then, keep practicing, and I'll see you soon, inshallah. Assalamu alaikum wa rahmatullah.